QGM. Anna talked about it already today, this morning. So QGM is a zero-dimensional model that calculates macroscopic plasma parameters like volume average, species densities, and electron temperature. So QGM calculates these parameters based on user-defined process conditions like pressure, power, the feed gas flow rates, and reactor dimensions. So why QGM is useful? So it's a 0D model, so it's fast. It solves only ordinary differential equations, so no partial differential equations are involved. So it's much faster than spatial models. Second, it's very simple, intuitive, so there's no need of detailed reactor geometry or special result boundary conditions, just simple process conditions. And finally, so it's not meant for specially detailed modeling, but it still can be very effective for quick assessments and for general exploration of trends in plasma behavior. But of course, there are drawbacks. So while QGM is very fast for a single case, it can still be very time-consuming for when performing large parameter sweeps. So when varying process conditions or feed gas composition, and additionally, so this makes it less suitable for optimization tasks when many evaluations are needed, and additionally, it requires predefined chemistry set. So what can we do to speed this up and to get the outputs of QGM faster? So we can substitute the global model with the surrogate machine learning model, so and approximate the outputs of the global model actually. So yeah, so still machine learning solution wouldn't be precise, but still it can be very useful to initialize plasma solvers closer to final solutions. Also, once machine learning model is trained, it's able to predict the outputs for like large input, a large set of input conditions very fast. So it makes the solution suitable for optimization tasks and real-time decision making when response time is critical. And so just to put it into perspective, so if we need to run global model simulations for 1,000 process conditions, we'll typically spend tens of hours doing that. But with a machine learning model, we can virtually predict all these, the outputs for all these instances virtually instantaneously. Okay, so to approach this task, we use supervised learning. So the goal of supervised learning is to map the input features to the target output based on some labeled data. So in our task, the input features noted as X here, the pressure, power, gas flow rates, the gas composition, the parameters, and reactor size, and the target outputs are the species densities and electron temperature. So yes, so for this task, we decided to focus on plasma mixtures containing fluorocarbons, argon, and oxygen. They're quite common in semiconductor processes such as etching of silicon-based materials like silicon dioxide, silicon nitride. They're useful in pattern transfer in advanced lithography and for wafer cleaning and surface treatment. And to train our machine learning model, we need to obtain a high-quality data set, so which captures the behavior of this plasmas under a realistic set of process conditions. So we chose two gas mixtures, one CF4 plus argon plus oxygen, and another one C4 F8 plus argon plus oxygen. So this choice of fluorocarbons just covers the opposite ends of the spectrum in terms of carbon fluorine content. And we ran global model at for about 3,300 unique process parameter combinations. And in terms of values, process conditions, we varied pressure between 10 and 200 pascals, and the power was changed between 100 and 1,000 watts. And as for feed gases, the flow rates were varied between 10 and 80 SCM per gas. And for reactor size, we kept it fixed for all simulations, both at 0.1 meter for both the reactor height and radius. Okay, so first we focused on predicting species densities. So for this, we used a feed-forward neural network. So the network just takes in 7 input parameters: power, pressure, the flow rates of feed gases, so argon, O2, and the fluorocarbon, and also additionally takes in the number of carbons and fluorine atoms per fluorocarbon. So, and well, in the output of the network is a set of different species densities. So we had 73 different species. So now I can show. I would like to show you the diagram of the machinery of the neural network that we use. So it's a fit-for-work neural network composed of 3 main parts: the input layer, the 2 hidden layers, and 1 output layer. So the input layer has had 7 nodes, every node for each input. The hidden layers, they were fully connected, and each of them had 1028 nodes. So this size was enough to allow the model to predict and to capture all the nonlinear relationships and data. And the output layer had 73 nodes, each for every species density. So how the neural network works. So each hidden node, it takes in weighted inputs from the previous layer, adds some bias, and passes the result of this through a nonlinear activation function. So, and during the process, during the neural network training, the weights and biases, they are adjusted with the so they adjusted with the goal to minimize loss function. So in our case, we used mean squared error. And also, so for training, we split data into 80% training, 10% validation, and 10% test set. And test set was not used in the process of training. It was kept aside, and it was only used for final validation. And also to prevent neural network overfitting, we used the early stopping strategy. So it's in this strategy, the neural network training, it stops automatically when the validation loss stops improving plateaus. So this helps the model to generalize well to new unseen data. Okay, so before training the neural network, we needed to perform some pre-processing steps. So first, all the density distributions in our test set, they looked like that. So they were highly right-skewed, and this is not ideal for machine learning. So we needed to perform logarithmic transformation. So here you can compare the distribution of CO densities in our test set. So it's very high, very right skewed. So we transform it when we perform logarithmic transformation, and now the values look by model shape. So they're smooth, well bounded, and we stabilize the variance. And also we performed the feature scaling. So we standardized them, we centered them around 0 and scaled to have a unit variance. So this also helps to stabilize the neural network training. And also we performed some neural network the post-processing steps on neural network outputs. So we applied some physical constraints. So we made sure that the ideal gas law was fulfilled, and also we accounted for charge balance. So we recalculated species densities, and we calculated the electron density as a net positive charge. So yes. Okay, so here, this figure, it presents the average relative errors for main species densities. So here we define main species as those with densities larger than 10 to the 15th power particles per cubic meter. So here we compare 2 cases. So the red bars, they represent the species densities coming from like raw neural network outputs, so no physical constraints. And the green bars, they represent the mean relative errors after applied post-processing. So we can see that applying ideal gas law and charge balances post-processing step, it helped reduce the relative error for most all major species, and overall the errors look quite good for for being a machine learning predictions. So next, we wanted to see how well the machine learning model generalized to a new fluorocarbon. So we tested it on a gas mixture that contained C2F6, argon, and oxygen. So here, the light brown bars, they represent relative errors for main species for the C2F6 argon NO2, and the green bars are the our relative errors from the original test set containing CF4, C4, F8. Yeah, so the dots here that represent individual test cases just for the feel of the error spread. So overall, of course, the errors for C2F6 they're quite large. So in some cases they reach 40-30%, but for most of the errors they are within 10-15%, which is quite good results. So only for C2F5 and C2F6 we have quite large errors, but yeah, it was also kind of expected because the species are well represented in this gas mixture. So to address this, the clear steps for improvement would be to include more fluorocarbons into our training set, like C2F6, and also introduce these gases that generate new target species, like C4, F6, so we can increase the output space for machinery model. Okay, and also apart from species densities, we wanted to predict electron temperatures. So in this case, we have the same input features, power pressure, the flow rates of feed gases, and the number of fluorine atoms and carbon atoms in fluorocarbon, but we only have one target variable, electron temperature. So here in this graph here, sorry, yes. So here you can see the distributions of electron temperature values in our train and test set, and they look very smooth and well bounded. So like we can use directly the electron temperature values for machine learning. Yes. So to select the machine learning model, actually, so we tested several conventional machine learning algorithms, and we also played with different neural network architectures. So to optimize the model parameters, we performed five-fold cross-validation. So we split our data set in validation and test set 5 times, and the model hyperparameters were adjusted with the goal of minimizing the error within these 5 splits. So the model is it can be like good for any types of missing data. So, and also to further improve generalizability and performance of our model, we used the voting regressor solution. So we combined 2 different algorithms into a voting regressor. So in this algorithm, 17% of predictions they come from the XGBoost algorithm, and 83% they come from support vector regressor algorithm. Okay, so here are the results. So the top graph shows the distributions of relative errors for log densities. Oh, sorry, not log densities, for electron temperature. So for the 2 gas mixtures, so you can see for both of them the errors are quite low. So for most of the test cases, they are below 1%, and yes, and for the average relative errors for both test cases are around like below 1.1%. And here the lower graph it shows the relative errors for the unseen gas mixture C2F6 plus argon plus oxygen, and of course they're way worse. The largest error that we got is 20%, but still for most of the test cases it's within 10-15%, let's say, and the average error of 8.27%, which is still a good result, let's say. So yes, this again highlights the necessity of including different fluorocarbons into our training set to improve the generalizability of the machine learning model. Oh, and also it's interesting to see and analyze which predictors were most important for machine learning models. So here the feature importances from 2 algorithms that we used. So these feature importances, they were calculated by randomly shuffling each feature and measuring how much the model performance drops when we just randomly shuffle the inputs. So the higher the drop in model performance, the more important is the feature. So interestingly for XGBoost, like absolutely most important feature is the number of carbons in fluorocarbons. So this you can see that in our voting regressor, XGBoost just helps to differentialize between 2 fluorocarbons basically. And as for the support vector regressor, the importance of features is more balanced. So the most important input is pressure, followed by the flow rate of fluorocarbon and the elemental composition of fluorocarbon. So, yes, small balance. So, just to conclude, the final takeaways from this work is that machine learning offers cost-effective and efficient alternative to simulations and obvious experiments. And our machine learning-based model predicts species densities and molecular temperature from process parameters with reasonable accuracy. And these predictions can be used to initialize plasma solvers for the final results. It would help to reduce computational time and performance. Thank you for your attention.